Welcome everyone. I'm Norman Wildberger. Today we're going to have some fun with polyominoes, which are very simple shapes made from little cells in our grid plane. And we're going to be counting polyominoes of certain forms, very small ones. We're going to be looking at some tiling puzzles involved with these, and we'll have a chance to talk a little bit about the subtleties in making appropriate definitions to steer us in the right direction. So these puzzles that we're going to talk about are very accessible to children in years K to 6. So I remind you, here's our grid plane, and we've already talked quite a lot about things like this. This is a rectangle, and this is also a rectangle, but they have slightly different shapes, although they look quite similar. This is a 1 by 3 rectangle, X is, while Y is a 3 by 1 rectangle. Strictly speaking, we say they have different shapes. And we can think of both of them as being constructed from little unit squares, or what we sometimes call cells, which are stacked together in a connected way. So we can go from one cell to the neighboring cell along an edge that they have in common. This is the motivating idea for a more general kind of object on the grid plane called a polyomino. So these more general shapes are formed by connecting cells along edges. So we insist that we're going to have a bunch of cells, and we can get from any one to any other by just moving sequentially across a common edge. So for example, this little object right here, these 3 cells together form a polyomino with 3 cells. We can go from here to here by going across this edge and then going across this edge from one square to another. Now, these polyominoes that we're considering here, these ones here, they're all a little bit like L-shaped ones. They're called trominos. In fact, all of these are trominos. They are the ones that have exactly 3 cells or 3 unit squares inside them. In fact, these are exactly the 6 tromino shapes. These are all different shapes because you can't translate from one to the other. It's also useful to look at the smaller polyominoes, which are just dominoes. So a 1 by 2 rectangle or a 2 by 1 rectangle, call that one H and that one V. They're also examples of polyominoes. So these are the kinds of objects that we're going to be looking at today, but we're going to be ending up considering a little bit more fancier, bigger ones. When we look at bigger ones, they get a little bit more interesting. And you've probably seen them before if you've played Tetris or if you've played Blokus, 2 very popular games. And now a very good initial question that we should ask ourselves is, when are we going to consider 2 polyominoes to be the same? There are at least 2 different possible ways of thinking about answering this question. One is in terms of a concept called shape, or same shape. Another one is a slightly related but different concept called same form. So let's have a look at the meanings of these words. In mathematics, we want to be careful about the meanings of words. This is a very good example here about how we're going to slow down and have a good look at how we're going to use words. So we're going to say that 2 polyominoes are the same shape when one is obtained from the other by a translation. So a translation is a movement that takes a polyomino, perhaps like this one here, and maybe moves it to the right a certain number of squares, or maybe moves it to the left, or maybe moves it up or down. Or perhaps it can move a combination of those directions, a certain amount to the right, a certain amount up. So for example, this polyomino A, which has 4 cells in it, and this polyomino B, which also has 4 cells in it, they look pretty close to being the same. In fact, if we take this A and we move it over 3 and then move it down 1, then we get exactly on top of B. So we say that A and B, these two polyominoes, are the same shape. There is one more polyomino in this collection here that is the same shape as A and B, and I hope you can find out which one it is. It's E right here. So this one, E, can also be obtained from either A or B by making a translation. These other ones look a little bit like E, B, and A, but we don't say that they have the same shape. We say rather that they have the same form. So we're going to use a different word now to denote the relationship between, say, A and C. So two polyominoes are said to have the same form if we can go from one to the other by a combination of translations, reflections, and or rotations. So for example, to go from D to E, we could get there by reflecting in this line here. A reflection takes D to E. Or if we take B and we rotate it by half a turn and then translate it, we get G. If we take B and we rotate it by a quarter turn and then move it, we get C. So we can get from A to any one of these polyominoes by a combination of translations, reflections, and rotations. So these all have the same form, while only these three have the same shape. And just as a little exercise, there is one more L-shaped polyomino that I haven't put on this list. See if you can find it. So before we start investigating these different types of polyominoes, we need a little bit of a criterion for how to distinguish them. And the most obvious one is the size of the polyomino. So if we have a polyomino called X, then we'll say that its size is the number of cells or unit squares that it contains. And this is the symbol that we'll use to denote the size of X. So if the size of X is 1, we're talking about a monomino, like this. If the size of X is 2, we're talking about a domino, which we've already talked about. That's a rectangle. Size is 3, then we're talking about a trimino, or sometimes called a triomino, but we'll use trimino. There's an example of a trimino, but it's not the only example. With 4 cells, we're talking about a tetramino. There's an example of a tetramino. With 5 cells, a pentamino. There's an example of one of them. 6 cells, a hexamino, something like this. 7 cells, a heptamino, something like this. And of course, we could carry on. And a natural first question, I think that almost everybody who thinks about these things will ask pretty soon is, how many different shapes or forms are there for each size? How many different shapes are there for a domino? How many different forms are there for a domino? How many different shapes for a trimino, or how many different forms can a trimino have? These are two different questions because there are more shapes than forms. Remember, for the triminos, we saw that there were 6 possible different shapes, because if we rotate this, we say that it has actually a different shape. But there were really only 2 possible forms for a trimino, namely this one here, or the one that we get by a rectangle, a 1x3 rectangle or a 3x1 rectangle. They're the same form. So one of these questions is a little bit easier than the other. The simpler question is to ask, how many different forms are there for each size? And that's a pretty interesting question. All right, so let's have a look at how many different forms are there for different sizes of polyominoes. If we're talking about size equals 1 or a monomino, well, there's only one possible form. It has to look like this. A domino, there's also only one form. It has to look like this. Because remember, this one and the vertical domino that you get by rotating it a quarter of a turn, they're considered the same form because one can be obtained from the other by rotation. In the case of size 3 or a trimino, there are these two different forms. And we might give them names. Might call this the form I and this the form L because they look a little bit like those letters. More interesting is when we get to the case of a tetramino, a polyomino with 4 cells. Well, it turns out that there are exactly 5 such objects. This one here, where they're all in a row forming a rectangle. This one here, which is an L-shaped one, give it the name L. This one here has a base of 3 with sort of 1 on top. That's naturally called a T. And this one here, called Z, which looks a little bit like a Z. It's got 2 on the bottom and 2 on the top. And this one here, which is just a square, we might call that O. Now, if you played Tetris, you will be quite familiar with these different shapes of a tetramino. And make sure that you stare at them and make sure that there's no other ones, that any other polyomino with exactly 4 cells is really one of these, perhaps rotated or reflected. Okay, now we come to a fun exercise. Obviously, it's good to think about the next step. And the next step is the case of the pentominoes, when we have a polyomino with 5 cells. So the exercise is list all the possible forms for a pentomino. I'll give you a hint. There are 12 of them. All right, that's a very good exercise. I'm going to show you the answer by the end of the video, but perhaps you'd like to stop the video at some point between then and now and figure this out yourselves. It's a great little fun thing to do with a piece of graph paper. All the possible ways of sticking 5 cells together to form a connected whole, where connection means connected across an edge. Okay, so now let's have a look at perhaps the first sort of interesting case, the case of the triminos. You have 2 types of triminos. What can we do with them? So it turns out that there's all kinds of interesting and fun questions when we talk about tilings with polyominoes. And what does that mean? Well, it means that we start off with some shape, perhaps this rectangle here, and we ask ourselves, how can we fill this thing up with tiles of the shape that we're considering? So imagine we have a whole box load of tiles, and you can actually think of real tiles that have this shape, and then another box that have tiles of this shape. You can use as many of these or these as you like, and you want to tile various things. Maybe your bathroom floor, or perhaps some more abstract shape like a rectangle like this. So in this case, there's 3 different ways of tiling this particular rectangle with triminos. One way is to use 2 I-shaped triminos laid one on top of the other, just like this. And the other 2 ways are to use 2 L-shaped triminos, one like this together with one like this, or essentially this one sort of flipped over, one like in this position and one in this position. 3 different ways of tiling this particular rectangle in terms of these 2 triminos. All right, how about a little bit more sophisticated question? Let's have a look at a 3 by 3 square. How many ways can we tile this thing with triminos? Well, one way would be to use the I tromino along layers. So one there, and one there. Another would be to stack them sort of vertically like this. Or we could use one of those, and then the rest of it reduces to one of these things, which we could tile in either this kind of way or this kind of way. So we could have this kind of tiling or this kind of tiling. Or we could do the same thing, but starting with the I shape on the right-hand side. And we could have these two different ways of filling in the rest. Or we could have the I shape sort of at the bottom, and there would be two different ways. Or the I shape up at the top. And altogether it looks like there are 10 different ways of tiling this particular square with trominos. And our second exercise is we have a little bit more elaborate bathroom wall. Now a kind of a big L shape like this, with altogether 2, 4, 6, 8, 10, 12 squares. And we want to tile this configuration with the trominos. And the question is, how many ways can we do that? So that's an exercise for you to work out. Now here's a famous puzzle which is due to Golomb, who was the mathematician who gave the name polyominoes to these objects, and he was one of the first people to sort of make a very systematic study of some of their properties. And here's a puzzle that he has that you need to show that if you start with a 4x4 chessboard and you remove any square from it, can be any one of these 16 squares, then the remaining portion can be tiled using just L's. No I's, just L's. So for example, here I've shown you how to tile the 4x4 square. If you remove this particular cell, there's an L right here that represents that L, 1, 2, 3. And then there's another L here, another L here, another one here, and one down here in this corner. Okay, so the first exercise is to show that you can do this no matter which of these cells you take away from the 4x4 square. A little bit more challenging is that actually the same is true for an 8x8 rectangle, or in other words, a chessboard. So if you take a chessboard and you remove any square from it, the rest of it can be tiled only using L's. So these are two exercises for you, and a challenge exercise, those of you who want a little bit more meaty kind of thing to think about. This is quite challenging. Show that the argument also works for a 16x16 rectangle. All right, 16x16 rectangle, the same is true. Any square you remove, the rest can be tiled with L's. So obviously things are going to get more fun when we get to tetrominos. So here are the 5 tetrominos that we've already talked about, and here are the names that we've given them: I, L, T, Z, and O. And I remind you, these are just the objects that appear in Tetris. And that's really a tiling game too, sort of a dynamical tiling game. Lovely game. So our first question is, can you tile a 4x5 rectangle with one each of these tiles? So each of the tiles has 4 cells, and there are 5 of these objects altogether. So altogether, the total number of cells is 4 times 5. So there are exactly as many cells in all of those as there are in this rectangle here. And the natural question is, well, can we take these 5, in other words, one of each of these, and arrange them so that they exactly tile this rectangle, so that every square is covered and there is no tile sticking out. For example, you might say, all right, let's stick this I down here, and then let's put this L. Well, we can move the L, we can maybe move it up here like that, and maybe we could fit a T in here. Keep going. Can we do it so that all the tiles end up being used? Well, the answer is no, you can't. You can't do that. And here's your next exercise. So you can stop the video after this and have a think about finding a reasonably simple explanation of why this is impossible. Of course, the first thing you're likely to do is to try it. And that's what you actually should do. You should try to do this. And you will be able to fit 2, 3, perhaps 4 of the tiles in. And then you'll find that the 5th tile doesn't fit into the remaining 4 cells that are empty. So you try some other arrangement. And again, you'll probably be able to fit 3 or 4 in. The 5th one doesn't fit. Try something else. You keep doing it. You eventually perhaps will start suspecting that this is true. But how do we know for certain? How do we know that there's not some really clever way of tiling this? So we're looking for some argument, some explanation for why this is true. See if you can come up with such an explanation. It's a bit of a challenge. So spend an hour or 2 thinking about this. Or maybe even a day or 2. It's worthwhile. So I hope you've gone away and thought about that little challenge problem. Now I'm going to give you an explanation. The idea is to use a checkerboard pattern to color cells. Think of this thing as being part of a chessboard or a checkerboard, colored alternately with, say, white and red. White, red, white, red, white. Every time we move horizontally or vertically, we change color. And think of the same kind of checkerboard pattern for each one of our 5 tetrominoes. So here we have, say, one color, let's say green, because it doesn't have to be the same as this color. Green, white, alternating. Green, white, alternating. Green, white, alternating. Green, white, alternating. This one here is a little bit different. Green, white, green, green, alternating. Or it could be white, green, white, white. Either way. But either way, what's going to happen is that there's something different about this one and all the others. Namely, these 4 have equal numbers of cells of each color. 2 greens, 2 whites. 2 greens, 2 whites, 2 greens, 2 whites, 2 greens, 2 whites. This one doesn't. It has an unequal number. It has 3 of one and 1 of the other. Either 3 greens and 1 white as I've drawn, or 3 whites and 1 green. So each of I, L, Z, and O has an equal number of cells of each color, but T does not. So if we use all 5 tiles exactly once, we must use an unbalanced number of red and white squares. This will be balanced between the 2 colors. So is this one, so is this one, so is this one. But this one will leave us with a lopsided number altogether. There will be more of one color used than another. But the thing that we're trying to cover has an equal number of reds and whites. That's the reason why this is impossible. That no matter how you arrange it, no matter how clever you are, the fact that there's going to be an unbalanced number of greens and whites when you move them over here, that's going to prevent you from actually fulfilling the task. That's why there is no tiling of the 4x5 rectangle with these 5 tetrominoes each used once. It's a lovely argument that illustrates an idea. The idea of using a checkerboard pattern, even though the original problem had nothing to do, it seemed to have nothing to do with checkerboards. We introduced that idea and then we were able to see a pattern, a reason why something didn't work. So please have a think about this lovely example of a mathematical argument. It's a mathematical argument. I hope it's convincing to you. So although we couldn't tile that 4x5 rectangle with each of the 5 tetrominoes used just once, what we can do is we can tile a rectangle which is twice as big if we use 2 copies of each tetromino. So here's a 5 by 8 rectangle, and here is an illustration of how to tile it with exactly 2 copies of each tetromino. So let's see if you can follow my picture here. So right here, up here, there's an eye shape, a rectangle of 4 in a row. And here's the second eye shape, another 4 in a row. The 2 squares, or the O shape, one here and one here. The 2 L shapes, well, there's one right here in green and another one here in green. The 2 T shapes, well, there's one here and there's another one here, just touching each other. And then there's the 2 Z shapes, there's one right there and one right there. So we've used each of the 5 tetrominos exactly twice. And we fill this 5 by 8 rectangle. Well, this is obviously a lot of fun, so you'll want to do the same kind of thing. So find a similar tiling of a 4 by 10 rectangle. 4 by 10 has the same number as 5 by 8. So we're going to try to find a tiling of this rectangle in the same way using 2 copies of each tetromino. Tetromino. And here's another exercise with a slightly different kind of shape. You might call it a castle. Can we tile this castle with all 5 tetrominos? So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 20 squares. So in terms of the numbers, there's a matchup. 5 times 4 is 20. Can you tile this thing with all 5 tetrominos used? So in our final slide, we'll have a look at pentominoes, the polyominoes with exactly 5 squares in them. And it turns out that there are 12 of them. And in fact, those 12 forms were known to ancient Go players. Go is a beautiful Japanese, Chinese, Korean board game. That's very popular in Asia and also in Europe and in America and elsewhere. And it's played on a grid-like board, and so it's not too unreasonable that shapes like this were investigated. So here are all 12 pentominoes, and they have names that sort of correspond to how they look. There's an F, an I, an L, an N, a P, a T, U, V, it'd be more a V if we tilted it. W, again, it'd be more a W if we tilted it. X, same. Y, and Z. And nice little exercise if you want to play around with these. Find tilings of some bigger rectangles, a 3 by 20, a 4 by 15, a 5 by 12, a 6 by 10 rectangle. Each one of those, try to find tilings using all 12 pieces. They all have 60 squares, so that works numerically, but whether you can actually fit them together, that is a bit of a challenge. So that's going to be a lot of work, and you might find yourself addicted to this kind of thing. If you do, well, there's lots of challenges on the internet. People have been playing around with these things for many decades, and it's a source of fun for a lot of people. So this is as far as we're going to go. Of course, it's natural to ask, what about hexominoes or heptominoes? How many of them are there? What kinds of tilings can we do with them, and so on? So we'll leave that for now. It's a fun little thing to investigate, but we're going to go back now to more standard arithmetic. We've seen the importance of counting and arithmetical operations, so it's necessary for us to develop some skill at these various operations. Next time we're going to start with the simplest operation of addition. We're going to learn how to systematically add. And we're also going to talk about the names of numbers. These two things are naturally related. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.